Okay, time's yours. Yeah.
Okay, hi everybody. My name is Jacques Nguessan, first year student here at UC Merced. My advisor is Dr. Sachin Goyal. And today I will talk about the stabilization of linear systems with distributed input delay and input saturation. So on today's agenda, we will have we'll first introduce the topic of distributed input delay and the saturation for inputs. Then we'll talk about the motivation of why I specifically wanted to look at this topic and talk about the problem statements that they have in the paper and the proposed solution and approaches that they use for these problems. So first, we have the topic introduction again, which will be about the distributed delay. So distributed delay are problems that arise in the modeling of control systems, and they are considered to be primary sources of instability and performance degradations. They are present in chemical, network, control, and biological system, and many other control systems. They are really practical, and they help to realize more realistic models of the system, but in a lot of cases, they sometimes are ignored. It's also due to the fact that they are challenging to design controllers for, because as you can see from the equation here, there are essentially infinite dimensional systems. So there are only very few results showing stability for said systems. Now, when it comes to saturation, it's also the same problem. So they are linked to instability and performance degradation inside of the system if they are ignored. But like the input delays, they are really practical and they have to be incorporated if we want to model the system accurately. And it's important to note that they are both complicated systems to model controllers for, but the combination of both the distributed delay and the saturation is even more difficult. And you have a case here of the system where we have saturation happening within the system with input delay, distributed input delay. So regarding the work that I looked at, prior to that, the authors were able to find only very few studies showing some semi-global stabilization. They were also able to work on one problem on their own and solve one of them when it comes to semi-global stabilizations. There was one or a couple of attempts made for stabilization of full global stabilization, but it resulted into controllers which had inside distributed terms, which were developed by using Lyapunov equations-based login feedback. But again, because of the distributed term, they are very difficult to compute. So the goal of the work that I focused on today, they were attempting to show that with some correct assumptions regarding the system, you should be able to stabilize the system by using steady state feedback. And by taking those assumptions into consideration, you should be able to derive some controllers by solving only linear matrix equations and not having distributed term inside of the controller. And they also wanted to show that the controller can achieve semi-globalizations. Semi-global stabilization when there is saturation inside of the input. So it's important to note that they worked on both invariant and variant time delay assumptions, but for the purpose of this class, I've solely focused on the time from the time invariant delay. So what is my motivation here? Like I said, I'm a student of Dr. Sachingola, and the previous work that we've developed, we were able to show that the increased response time introduced by Parkinson's disease causes some tremors within the person affected by the disease. So as you can see here, the body has a prescribed velocity, but thanks to the transport delay and the added saturation, it causes tremor within the patient's body. So that's the main motivation why I wanted to focus on this area of linear time invariant systems. So what are the problems that they investigated into in this paper? The first one is the global stabilization problem. So looking at a system having a distributed input delay, they wanted to be able to find a controller U of t such that the resulting closed loop system is asymptotically stable. And again, like I've mentioned, they both explored the time variant and time invariant case, but I decided to focus on the time invariant for now. The second problem investigated was the semi-global stabilization when it came to saturation into the input. So given a bounded delay tau and a set of initial values, they wanted to be able to find a controller to have the closed loop system to be asymptotically stable at the origin of the given set. So how did they do that? So looking at the problem one, the solution, they first introduced a capital B matrix here that was under this form. And using, basically saying that A and uppercase B were stabilizable, the system A, uppercase B was stabilizable, and the poles of A being on the closed left half plane, they were able to draw an assumption saying that all the eigenvalues of A are on the imaginary axis, and that the system A uppercase B is controllable. Again, like we said, we're not gonna bother really with the proof here, but they essentially broke down the system like so, and where A naught is asymptotically stable and AS is asymptotically stable and A naught is made has eigenvalue lying on the imaginary axis. And from there, they were able to prove that the stability of this system was linked to the controllability of the first system here, showing again that the eigenvalue had to be on the imaginary axis. After they got that first assumption, they were able to say that if the assumption is in fact satisfied, then for any given delay tau, there exists a gamma, which is a function of tau, and allows us to get a family of linear state feedback, U of t, basically, again, state feedback here, taking this form, minus uppercase B transpose P of gamma X of t, which solved the first problem. Again, the first problem is sorry about that. The first problem is to find the controller T so that the closed loop system here is stable. And they, again, like we've mentioned, they were trying to get those controllers by solving linear matrix equations. And here the P matrix is the solution, is positive definite, and is the solution for the algebraic Riccati equation given by this equation here. So again, not gonna bother really with the proof here, but essentially they use Lyapunov function to show that in accordance with some matrix inequalities, they were able to conclude that the limit of as t goes to infinity here will be equal to 0, and therefore the system is asymptotically stable. So gamma here in the paper was, they were able to compute gamma using this equation. Yes, this equation, but that estimate was not necessarily true. So they used some trial and error method to get a range for gamma. And once the range of that interval was reduced enough so that the two values were very close, they were able to use those to find the feedback gain. They also showed that you could use a tool that is also incorporated in MATLAB called the DDE BIF tool that will allow you to find the different values for gamma also. And again, they briefly mentioned that through a similar process, you could also do that for output feedback. So you're not necessarily stuck with state feedback control here. So the proposed solution for problem number 2, again, problem number 2 is the semi-global stabilization when we introduce saturation in the input. It's also based on the first assumption. Essentially, the controller used for problem number 1 also solved problem number 2. And P, again, is the solution, is a positive definite matrix, which is the solution of the algebraic Riccati equation given here. And to reiterate, the gamma here is within a set given here that you are able to calculate to get from this equation. And again, this is only for to make the closed loop system stable, but for semi-global stability. And the domain of attraction, from what I could gather, is a set of initial state vector from which tracking is feasible. So the proof, again, is similar to proof number 1, where they use a Lyapunov function and some inequalities. They were able to get to conclude that this will be smaller than 1. Therefore, the closed loop system would never saturate and remain linear. And again, this is the definition of the saturation function. So as you can see here, it's max by 1. After that, they wanted to show a numerical example for the system. So they introduced this system here with the system matrix A and control matrix B. They were able to prove that A and B were controllable for beta here being greater than 0 and tau, the delay, greater than 0. They also have omega here being 2. And as you can see, the delay in the system is fairly large with 1 second. So using the formula I showed before, they were able to determine what the values for gamma were, at least an interval for that. And they were able to find the feedback gains for gamma. This is the feedback gain for gamma is equal to 0.5. And those are some results. So for the different gammas, they were able to find the different states of the system. And as you can see, they are all asymptotically stable. So again, those are the closed loop system states. Then those are the control signals for the different values of gamma here. They also wanted to show that beyond a specific threshold, gamma will make the system unstabilizable. So after a threshold, again, you can see that the states are unstable. Now they wanted to mention that the assumptions that they have is fairly strict, but is vital for the existence of the solution for problem 1. And again, the assumption is that the eigenvalues of A are on the imaginary axis. And they are, you can essentially change the assumption if you have more information for B in function of sigma here. And therefore the assumption can be relaxed. The analysis, however, will turn out to be more complicated. So, and the conclusion drawn might not be relevant. However, so this paper was published in 2012, so maybe by now they also have different results, because I did mention that they wanted to explore more general cases here. And again, I think for the final report that we submit for this study, I would like to try to look at a system that we developed in one of the papers previously worked by Dr. Goyal, where they have a system similar to this. The transfer delay is not necessarily a distributed one, but because the distributed one is supposed to be a general form of delays in the input, I believe there should be some relationship here that I could use to work an example for the final report. Are there any questions?
Very good. Can you revisit what is the gamma? Did you do the Simulink simulation yourself?
Which
so those Simulink results is plots.
No, so those plots were provided in the paper.
Oh, in the paper, okay.
I will so like I said, I want to work a model based on this, because in a previous paper we were able to develop a SISO system using this. So, and in the paper they were showing also a SISO system. Mm-hmm. So I wanted to maybe derive some parallels there and maybe try to get some values for the report.
Can you go back and revisit what is the gamma?
Yes, sorry. So gamma here.
Oh, okay.
So gamma is a constant that they introduce.
I see.
For
yeah, we missed many details here. What is the phi then?
The phi is a function of the delay and the gamma, and it's related to the dimensions of the system, n and m. I guess I should have. It's using the proof of the theorems. Mm. So
yeah, I would make because you have space here. I would make the slides more self-containing instead of going to the original paper and find out the meaning of each symbols. But I'm fine with that. So please enhance the slides. Try to make it more self-containing. Okay.
Okay.
Without asking the readers to go back to check each symbol and what's that. So you can do a reminder. You did a good job in doing slides. So everybody listen, this is a way to introduce a paper combining your own perspectives, like how I can make use of the results. So I like the style of the presentation. So, but technically you can zoom in and make all the symbols explained. Okay.
Okay, I'll make sure to
Yeah.
do
In the
that
final
for
writing, you have to be self-containing. Okay. You can be more detailed than more detailed than the paper itself. Okay.
Okay.
So anybody you got a question? And I think his project on a PD patients understanding the overall motor control loop with delay and saturation is. I also believe that the delay is not a single delay; it should be a distributed delay, isn't it?
Yes, and also I guess because it's true that the delay increases as the disease progresses, so it will also be a time variant case.
Have you seen anybody did any modeling or control work considering this type of picture? The delay is distributed, or did you search the PD Parkinson disease versus a distributed delay? Is this already in the literature or not?
When I reproduce the results of the paper, I don't think they had distributed. It was just a discrete delay that I used to reproduce the results.
That's great. That's great. So it's excellent. So if you publish anything on the distributed delay for Parkinson's disease, you should acknowledge ME-210. Okay.
Okay.
Okay. Good job. This is the purpose of using the coursework to stimulate your research. This is what exactly I wished. Okay.
Okay.
So if you guys don't have any questions in the interest of time, I'm going to switch to the next one. I'm going to pause.